Good morning everyone. Myself I'm Likita from CSIT and my topic is System of Equations. Let's start with the introduction of the topic. In mathematics, a set of simultaneous equations, also known as a system of equations or an equation system, is a finite set of equations for which common solutions are sought. An equation system is usually classified in the same manner as single equations, namely as a system of linear equations, system of nonlinear equations, system of bilinear equations, system of polynomial equations, system of differential equations. Let's know about system of linear equations. In mathematics, a system of linear equations or a linear system is a collection of one or more linear equations involving the same set of variables. For example, 3x plus 2y minus z equals to 1, 2x minus 2y plus 4z equals to minus 2, minus x plus 1 by 2y minus z equals to 0 is a system of three equations in the three variables x, y, z. A solution to a linear system is an assignment of values to the variables such that all the equations are simultaneously satisfied. A solution to the system above is given by x equals to 1, y equals to minus 2, z equals to minus 2 since it makes all three equations valid. The word system indicates that the equations are to be considered collectively rather than individually. In mathematics, the theory of linear systems is the basis and a fundamental part of linear algebra, a subject which is used in most parts of modern mathematics. Computational algorithms for finding the solutions are an important part of numerical linear algebra and play a prominent role in engineering, physics, chemistry, computer science, and economics. A system of nonlinear equations can often be approximated by a linear system. See linearization, a helpful technique when making a mathematical model or computer simulation of a relatively complex system. Very often, the coefficients of the equations are real or complex numbers and the solutions are searched in the same set of numbers, but the theory and the algorithms apply for coefficients and solutions in any field. For solutions in an integral domain like the ring of the integers or in other algebraic structures, other theories have been developed. See linear equation over a ring. Integer linear programming is a collection of methods for finding the best integer solution when there are many. Grobner basis theory provides algorithms when coefficients and unknowns are polynomials. Also, tropical geometry is an example of linear algebra in a more exotic structure. Trivial example. The system of one equation in one unknown 2x equals to 4 has the solution x equals to 2. However, a linear system is commonly considered as having at least two equations. Simple non-trivial example. The simplest kind of non-trivial linear system involves two equations and two variables. 2x plus 3y equals to 6, 4x plus 9y equals to 15. One method for solving such a system is as follows. First, solve the top equation for x in terms of y. X equals to 3 minus 3 by 2 by y. Now substitute this expression for x into the bottom equation. Then we'll get 4 of 3 minus 3 by 2y plus 9y equals to 15. This results in a single equation involving only the variable y. Solving gives y equals to 1 and substituting this back into the equation for x yields x equals to 3 by 2. This method generalizes to systems with additional variables. See elimination of variables below or the article on elementary algebra. Let's see about general form of an equation. A general system of m linear equations with n unknowns can be written as a m1 x1 plus a m2 x2 plus so on a mn xn equals to bm as shown in the figure. Often the coefficients and unknowns are real or complex numbers, but integers and rational numbers are also seen as are polynomials and elements of an abstract algebraic structure. Let's know about vector equation. One extremely helpful view is that each unknown is a weight for a column vector in a linear combination. This allows all the language and theory of vector spaces to be brought to bear. For example, the collection of all possible linear combinations of the vectors on the left hand side is called the span, and the equations have a solution just when the right hand vector is within that span. If every vector within that span has exactly one expression as a linear combination of the given left-hand vectors, then any solution is unique. In any event, the span has a basis of linearly independent vectors that do guarantee exactly one expression, and the number of vectors in that basis cannot be larger than m or n, but it can be smaller. This is important because if we have m independent vectors, a solution is guaranteed regardless of the right hand side and otherwise not guaranteed. Let's see matrix equation. The vector equation is equivalent to a matrix equation of the form Ax equals to b, where A is a m into n matrix, x is a column vector with n entries, and v is a column vector with m entries. The number of vectors in the basis of the span is now expressed as the rank of the matrix. And we can see the matrix equation form in the image. Let's see about the solution set. A solution of a linear system is an assignment of values to the variables x1, x2, so on xn such that each of the equations is satisfied. The set of all possible solutions is called the solution set. A linear system may behave in any one of three possible ways. The system has infinitely many solutions. The system has a single unique solution. The system has no solution. Here is the example for single solution. Geometric interpretation. For a system involving two variables x and y, each linear equation determines a line on the xy plane because a solution to a linear system must satisfy all of the equations. The solution set is the intersection of these lines and is hence either a line, a single point, or the empty set. For three variables, each linear equation determines a plane in three-dimensional space and the solution set in the intersection of these planes. Thus, the solution set may be plane, a line, or a single point, or the empty set. For example, as three parallel lines do not have a common point, the solution set of that equation is empty. The solution set of the equations of three planes intersecting at a point is a single point. If three planes pass through 2 points, their equation have at least two common solutions. In fact, the solution set is infinite and consists in all the line passing through these points. For n variables, each linear equation determines a hyperplane in n-dimensional space. The solution set is the intersection of these hyperplanes and is a flat which may have any dimension lower than n. In general, the behavior of a linear system is determined by the relationship between the number of equations and the number of unknowns. Here, in general means that a different behavior may occur for specific values of the coefficients of the equations. In general, a system with fewer equations than unknowns has infinitely many solutions, but it may have no solution. Such a system is known as an undetermined system. In general, a system with the same number of equations and unknowns has a single unique solution. In general, a system with more equations that unknowns has no solution. Such a system is also known as overdetermined system. In first case, the dimension of the solution set is in general equal to nm, where n is the number of variables and m is the number of equations. The solution set for two equations in three variables in general is a line. The following pictures illustrate this trichotomy in the case of two variables. The first system has infinitely many solutions, namely all of the points on the blue line. The second system has a single unique solution, namely the intersection of the two lines. The third system has no solutions since the three lines share no common point. It must be kept in mind that pictures above show only the most common case, that is the general case. It is possible for a system of two equations and two unknowns to have no solution if the two lines are parallel, or for a system of three equations and two unknowns to be solvable if the three lines intersect at a single point. A system of linear equations behave differently from the general case if the equations are linearly independent or if it is inconsistent and has no more equations than unknowns. Let's know the properties of equations. Independence, consistency, equivalence, solving a linear system, describing the solution, elimination of variables, row reduction, Cramer's rule, matrix solution. Let's start the next topic, nonlinear system. In mathematics and science, a nonlinear system is a system in which the change of the output is not proportional to the change of the input. Nonlinear problems are of interest to engineers, biologists, physicists, mathematicians, and many other scientists because most systems are inherently nonlinear in nature. Nonlinear dynamical systems describing changes in variables over time may appear chaotic unpredictable or counterintuitive, contrasting with much simpler linear systems. Typically, the behavior of a non-linear system is described in mathematics by a non-linear system of equations, which is a set of simultaneous equations in which the unknowns or the unknown functions in the case of differential equations appear as variables of a polynomial of degree higher than 1, or in the argument of a function which is not a polynomial of degree 1. In other words, in a nonlinear system of equations, the equation to be solved cannot be written as a linear combination of the unknown variables or functions that appear in them. Systems can be defined as nonlinear regardless of whether non-linear functions appear in the equations. In particular, a differential equation is linear if it is linear in terms of the unknown function and its derivatives, even if nonlinear in terms of the other variables appearing in it. As nonlinear dynamical equations are difficult to solve, nonlinear systems are commonly approximated by linear equations. This works well up to some accuracy and some range of the input values, but some interesting phenomena such as solitons, chaos, and singularities are hidden by linearization. It follows that some aspects by dynamic behavior of linear system can appear to be counterintuitive, unpredictable, or even chaotic. Although such chaotic behavior may resemble random behavior, it is in fact not random. For example, some aspects of the weather are seen to be chaotic, where simple changes in one part of the system produce complex effects throughout. This nonlinearity is one of the reasons why accurate long-term forecasts are impossible with current technology. In mathematics, a linear map f of x is one which satisfies both the following properties: additivity or superposition principle, f of x plus y equals to f of x plus f of y; homogeneity, f of alpha x equals to alpha into f of x. Additivity implies homogeneity for any rational alpha and for continuous functions for any real alpha. For a complex alpha, homogeneity does not follow from additivity. For example, an antilinear map is additive but not homogeneous. The conditions of additivity and homogeneity are often combined in the superposition principle. F of alpha x plus beta y equals to alpha f of x plus beta f of x. An equation written as f of x equals to c is called linear if f of x is a linear map and non-linear otherwise. The equation is called homogeneous if c equals to 0. The definition f of x equals to c is very general in that x can be any sensible mathematical object, number, vector, function, etc. And the function f of x contains differentiation with respect to x. The result will be differential equation. Let's know about nonlinear algebraic equations. Nonlinear algebraic equations, which are also called polynomial equations, are defined by equating polynomials to 0. For example, x square plus x plus 1 equals to 0. For a single polynomial equation, root finding algorithms can be used to find solution to the equation. However, systems of algebraic equations are more complicated. Their study is one motivation for the field of algebraic geometry, a difficult branch of modern mathematics. It is even difficult to decide whether a given algebraic system has complex solutions. Nevertheless, in the case of the systems with a finite number of complex solutions, these systems of polynomial equations are now well understood and efficient methods exist for solving them. Non-linear recurrence relations. A non-linear recurrence relation defines successive times of a sequence as a non-linear function of preceding terms. Examples of non-linear recurrence relations are the logistic map and the relations that define the various Hofstadter sequences. Non-linear discrete models that represent a wide class of nonlinear recurrence relationships include the Narmax model and related nonlinear system identification and analysis procedures. These approaches can be used to study a wide class of complex nonlinear behaviors in the time, frequency, and spatio-temporal domains. Non-linear differential equations. A system of differential equations is said to be a non-linear if it is not a system of linear equations. Problems involving non-linear differential equations are extremely diverse and methods of solution or analysis are problem dependent. Examples of non-linear differential equations are the Navier-Stokes equations in fluid dynamics and the Lotka-Volterra equations in biology. One of the greatest difficulties of non-linear problems is that it is not generally possible to combine known solutions into new solutions. In linear problems, for example, a family of linearly independent solutions can be used to construct general solutions through the superposition principle. A good example of this is one-dimensional Hart transport with Dirichlet boundary conditions, the solution of which can be written as a time-independent linear combination of sinusoids of differing frequencies. This makes solution very flexible. It is often possible to find several very specific solutions to nonlinear equations. However, the lack of superposition principle prevents the construction of new solutions. Let's start the topic system of bilinear equations. In algebra, systems of bilinear equations are collection of equations, each one of which is written as a bilinear form, for which a common solution is sought. Given one set of variables represented as a vector x and another represented by a vector y, then a system of bilinear equations for x and y can be written as y power t aix equals to gi. Here I is an integer whose value ranges from 1 to some upper bound r. The AI are matrices and GI are some real numbers. Systems of bilinear equations arise in many subjects including engineering, biology and statistics. We consider here the solution theory of bilinear equations in integers. Let the given system of bilinear equation be as shown in the image. This system can be written as, once we solve this linear system of equation, then by using rank factorization below, we can get a solution for the given bilinear system as given. Now we solve the first equation by using the Smith normal form. Given any m into n matrix A, we can get two matrices U and V in SLM and SLN respectively, such that UAV equals to D, where D is as follows, where di is greater than 0 and di det di plus 1 for I equals to 1, 2, so s minus 1. Given a system Ax equals to B, we can rewrite it as dy equals to C, where Vy equals to X and C equals to UB. Solving dy equals to C is easier as the matrix D is somewhat diagonal since we are multiplying with some. Since we are multiplying with some non-singular matrices, the two systems of equations are equivalent in the sense that the solution of one system have one-to-one correspondence with the solutions of another system. We solve dy equals to c and take x equals to vy. Let the solution of dy equals to c be y equals to a1 b1 st, where st are integers, are free integers, and these are all solutions of dy equals to c. So any solution of ax equals to b is vy. Let v be a given by v equals to 11 so on as given in the image. We want matrix M to have rank 1 so that the factorization given in second equation can be done. Solving quadratic equations in two variables in integers will give us the solution for a bilinear system. This method can be extended to any dimension, but at higher dimension solutions become more complicated. This algorithm can be applied in Sage or MATLAB. Let's start with system of differential equations. In mathematics, a system of differential equations is a finite set of differential equations. Such a system can be either linear or nonlinear. Also, such a system can be either a system of ordinary differential equations or a system of partial different equations. Linear system of differential equations. Like any system of equations, a system of linear differential equations is said to be overdetermined if there are more equations than the unknowns. For an overdetermined system to have a solution, it needs to satisfy the compatibility conditions. For example, consider the system as given, then the necessary conditions for the system to have a solution are as shown. Nonlinear system of differential equations. Perhaps the most famous example of a nonlinear system of differential equations is the Navier-Stokes equation. Unlike the linear case, the existence of a solution of nonlinear system is a difficult problem. Thank you.